All right, so now we're going to talk about mathematically what does it mean for a function to be continuous. Okay, so I want you to know that continuous really does mean drawing without lifting your pen. Drawing a function without lifting your pen. So we're going to find a math way of saying that. And this is encapsulated. So this says it's continuous at this point A if when I take the limit as x goes towards a of the function, I land on f of a. All right, so this can break down into three parts. I'm going to want you to know all the three parts because that's how we're going to show something is not continuous. So here we go. So if the function will be continuous at a point A, if f of a is defined, so there's at the x equal a, there is a y value that goes with it. If when I take the limit as x goes towards a of the function, it exists as a finite number. So not infinity is what's implied there. And when I take the limit as x goes to a of f of x, I get f of a. Okay. So we need to say, give a reason, so a mathematical reason why it's not continuous. So you saying there's a hole or a jump is not okay. No credit will be given for those. You can see that it's not continuous by a hole or a jump, but you'll need to use one of the three-part definitions. Okay, so it's called a removable discontinuity, or when there's a hole in the graph. So let's talk about what that looks like. So we've been doing graphs like this. So let's look at y equals, or f of x equals, x squared minus 9 over x plus 3. If x does not equal negative 3. And 4, if x does equal negative 3. Okay, we've done things like this before, but let's just go over this. X plus 3. X minus 3 over x plus 3. That gives me y equal x minus 3. So it looks like this, y-intercept of negative 3. So when x is negative 3, right, because I canceled these, when x is negative 3, I have a hole in the graph. So there's a hole down there, and we can know what that y value associated with that hole is by putting negative 3 into here, so I get negative 6. All right, I've done that kind of in the corner, so let me just draw it over here again. So I have a hole here that's at negative 6, negative 3. All right, and so this says when x is negative 3, I get the y value of 4. All right, so this is obviously not continuous. There is a hole. And it's called a removable discontinuity because I could easily fill in the hole by redefining the function. So what is the mathematical reason for there not being continuous? What you would say is if I take the limit as x goes towards negative 3 of the function, it does not equal f of negative 3. F of negative 3 is defined as 4, right? When I plug in x equal negative 3, I get that 4. And when I take the limit as x goes to negative 3 on this function, right, go from both directions, I get the y value of negative 6. Those are not equal to each other. So you need to say all of this. This is necessary to say this is not equal to this. Tell me what this is equal to. Tell me that what this is equal to. So this is the mathematical reason to say this is not continuous. All right, so when there's a jump in the graph, then we're looking at when the graphs don't equal each other, the limits don't equal each other. So let's look at, if I made up a function, f of x is absolute value of x over x. If x does not equal 0, 2 if x does equal 0. Okay, so explain why this is not continuous at x equals 0. So if I was to draw this, you know, this is that graph. That's 1 and that's negative 1, and this is making a definition at 2 here. Okay, so the reason I would say this is not continuous, I would say as I take the limit as x goes towards 0 from the left, I get negative 1. And if I take the limit as x goes towards 0 from the positive side, I get 1. So therefore, the limit as x goes towards 0 does not exist. So if I was to think about what reason, that means this limit has to exist in order for it to be continuous, and it doesn't exist because I know the definitions. If I take the limit from the left and the right, they don't equal each other. All right, an infinite discontinuity would be an example if I had 1 over x if x didn't equal 0, and 3 if x equaled 0. So if I was to draw this, it would look like that, right? Okay, so if I take the limit as x goes towards 0 from the positive side, I get infinity. So since it's not finite, therefore it's not continuous. Right, so I get an infinite discontinuity. All right, so these are just words that we use to describe the discontinuity, but you need to give the mathematical reason to get credit. I just want to make sure you really know it's these 3 that are going to tell you whether it's continuous or not. Those are the 3. So these descriptions are just for us to know which kind of discontinuity we're looking at. All right, so it'll always say use the definition of continuity, and you'll always be given a point of where to show which one it is. So let's pause here and continue on the next video.